question 9 and 10 are, let me see, kind of similar, right? Question 9, which compound has the lowest solubility? So we know what like dissolve like. And the water is the most polar solvent. So which one has the lowest solubility? That means lowest solubility. That means what? Least polar. Or we can say most non-polar. Or we can say have most non-polar bonds. Non-polar bonds. And then most non-polar bonds means what? How we determine polar bonds? So the difference between electronegativity, right? Most non-polar bonds means least electronegativity difference. Least electronegativity difference. Because only large electronegativity difference will lead to polar bonds. Why is that? Because if one has very strong capability of attract electrons and one has very weak, then when they are together, one grab all the shared electrons. Then it's polar. One is very positive, the other is negative. So we call it bipolar weather. What does it mean? It means hot weather and then cool or cold weather in the same day. If the temperature does not change much, then it's non-polar, right? It's non-polar weather. The same thing here. Then we can see diethyl ether. And methylpropyl ether. One butanol. So it has OH group. Okay, surely it's more polar than this, right? Because it has OH group. Then when it has OH group, it's very polar. And then the compound 4, so the compound 4 has 2 OH group, right? 2 OH group. Here I will save time. I will not just draw them. 1, 2, 3, 4. Okay. This is compound 4. And the last compound is pentane. Right? Surely this one has the lowest electronegativity difference because it has only carbon and hydrogen. And then the carbon and hydrogen, the electronegativity difference is only 0.4, 2.5 minus 2.1, 0.4. So this one has the least electronegativity difference. Then is the least non-polar, or we can say the most, the least polar, and we can say most non-polar. Then most non-polar among 5 of them. Then we contact with the most polar solvent, water. It has the least solubility, like dissolve like. You see that? The same thing. And then for, so which one will, for question 10, which one will have the highest? This one, because it has 2 OH group. So make this whole molecule the most polar among these 4. And question 11 is also related, and we can see which one have the highest boiling point. This one, because it has two hydroxy group. It has two hydroxy group. These two properties are related. The more OH group, the more polar. And then the higher solubility in water, because water is the most polar solvent and the like dissolved like. And then because it has two OH group, the hydrogen bonding is also the strongest. Hydrogen bonding. Hydrogen bonding is the strongest intermolecular forces. Now, the ionic bond sure is stronger than that, but ionic bond only exists in what? In salt, not in these organic molecules. Okay. So this one will also have the highest boiling point. Highest boiling point. So question 12. Question 12. Which of the following cannot be synthesized? This compound, 2-bromine pentane. So question 12. 2-bromine, 2. Here's bromine. And the compound is the B reaction cannot. Why is that? Let's take a look. B is 2-pentane. You see, cannot be used to synthesize efficiently. Okay, so here. There are two possibilities, right? Hydrogen attack here. When you attack here, we get a positive charge here. And then if you attack here, we get a positive charge here. You see that? They are both secondary carbocation. Therefore, they are not much different in terms of what? Stability. Therefore, both of them can occur. Maybe this one is slightly more stable. So maybe 60% of this and 40% of this. Then you will get a mixture. So from here you get this. And from here you get this. You get a mixture. Why? Because they are not much different in terms of the stability. They're both secondary carbocation. They're both secondary carbocation. Okay. Then here, assignment 6. Question 1. You see, first we'll take a look at this. We see, oh, this methyl group and hydroxy group, then it's not a symmetrical structure. Then it cannot be methyl. You see that? Even though they may have opposite chirality, they cannot cancel. Why? Because they have different extent of R or S chirality. So methyl structures only apply to those symmetrical structures, and these are not symmetrical. So they cannot. And then here we can see these both carbons are chiral, right? And then if this, so here we don't need to spend time identifying the chiral. So if this is R, this is R, this must be X, this must be X. Or you can say this is R, S, and then this is R. They are just enantiomers, right? Because they are just mirror images of each other. Why is that? So here, the structure for both of them, you see that here, there's one hydrogen here, right? And then there's one hydrogen here. So we just switch, when you switch these two, the chirality switches, right? So you don't need to spend time trying to figure out. Because here, from here, for this current, for these two currents, you just switch these two groups. When you switch these two groups, you change the chirality. So therefore, these two currents have opposite chirality, and these two currents have opposite chirality, and each of them is not symmetrical structure. Therefore, we don't need to figure out this RNS. Even though the other one is R, the other S, the chirality cannot cancel. It's different from this case. Okay, it's different from this case. The chirality cannot cancel. And then for this, okay, for question 2, you can see that there's this is the plane of symmetry, or we call symmetry of plane, same thing. Okay, there's a symmetry of plane. You see that, why? Because there's a plane here that can cut these two structures, this structure into half, and the left and this part and this part are the same, See that are the same. Therefore, it must be a methyl compound. When they are methyl compound, they must have opposite chirality. They must have opposite chirality. So if this is R, this must be S. But so they must have opposite chirality. Okay. And here we can easily see only D proton. Because only D has two opposite chirality. But one thing we need to keep in mind is that for question 2, so yeah, we have discussed this many times, but I think it's worth to discuss more. You see, here is OH group. This is OH group. Again, you will see there's a symmetry plane. Again, right? And then these two also have opposite chirality. So if this is, let me see, if that is R, it could be S. Okay, here I will not spend time. If that one is R, then this must be S. If that one is S, this must be R. These two compounds are the same compound. These two compounds are the same compound. You cannot say you cannot say, oh, they are enantiomers. You can look at this. They have the same connectivity, right? And then they have the same chirality, because one is R, the other is S. One is R, the other is S. So this is a methyl compound. And this is also a methyl compound. These two are the same thing. These two compounds are the same. And it's not chiral. It's not chiral, right? Because these two is a symmetrical structure, and their chirality can cancel. Okay, or organic chemistry is not easy. Organic chemistry is not easy. Organic chemistry and physical chemistry are very different. Or the most different. Maybe analytical chemistry could also be different, but it is just my own opinion. Organic chemistry is not easy. You see that these two compounds are the same. Yes. So we cannot be misled by this drawing. What really matters is the chirality. This R is S, right? Because there's a plane of symmetry here that cut them into halves. And the chirality cancel is not chiral. Same thing for that compound. It's not chiral. It is methyl compound. The chirality, these two chirality cancel each other. And they have the same connectivity. So So it's not chiral. Then these two compounds are the same. But if you change one into this, if you change one, so this OH. You know, this, well, a regular way is to figure out the chirality using what we have learned. But normally what I do, when I look at this, I know if this hydroxyl group is out of plane, then it's a methyl compound. Then they have opposite chirality. And now, this is behind the plane, this is out of plane, then it is not methyl compound. Then I'm sure they should have the same chirality. So maybe kind of back and forth. So these two must have opposite chirality. Then we work on this. You don't need to spend time do this, follow the way we just discussed to figure out the chirality. You can see this is a symmetrical compound. There's a symmetry plane. Then it's a methyl compound. The chirality cancel. The chirality of these two chiral centers cancel. Then must have opposite chirality. Then we directly go to the correct answer. So I'm sorry, this one is not methyl. So when this is also out of plane, methyl. And this may not be S, but they have opposite chirality. Okay, we need to keep this in mind. Because there's a mirror plane that cuts this into two identical halves. They must have opposite chirality. Which method provide, question 3, which method provide the best synthesis of ethyl isopropyl ether? So ethyl ether is, we have so for compound A, we have this. So this is negative, this is positive. Then we have this. This is what? This is the primary alkyl halide. We know this is a strong nucleophile, but also strong base. Okay. So even though this is strong base, but this is primary alkyl halide, then the elimination reaction is not preferred. So substitution reaction is preferred. So this one can work, because this can attack here, and then we get the desired product. What about B? B, we get so this is a strong base, we also know. And this is what? Sorry, this is primary. This is secondary. Then this is a secondary alkyl halide, and this is strong base. So there's a possibility of SN2, substitution reaction, and what? Basically, the substitution reaction and the SN2 and the substitution reaction and the elimination reaction are in competition. Could be a mixture. So in competition. Why? Because this is secondary alkyl halide. For primary, the elimination is not preferred. Is not preferred. And then that could, and so compared to this one, compared to the option A, this is not desired. Why? Because there are two reactions in competition. Because this is secondary alkyl halide. For secondary alkyl halide, so elimination is a good option. At the same time, substitution is also an option. So they are in competition. So that's not the best choice. So for C, right? For C at 140 Celsius degree, let me see. Remember what we discussed, 140 Celsius degree. 140 degree, it did, there's one slide. Ether. You see that? So at 140 Celsius degree is this the reaction? But the problem is that 140 Celsius. I mean, for option D at 180 degrees is what is the elimination, right? Is the elimination reaction. So option D is not right. But for option C, option C is that it could lead to a mixture, right? The ether, symmetrical. Yeah, here, you see that? If you use, if you use different alcohols, then you will get a mixture. Why? Because this alcohol can react with itself, and this alcohol can react with itself, and they can react with each other. Then we'll get a mixture. So that's the reason. Option C is not. Option C is not good either. Option C is not good either. Okay. And option D, because at a higher temperature, as we have done this experiment in lab 7 in last semester, it will be an elimination reaction. Okay, elimination reaction. So what about E? E we get this is again, this is OH group. It's secondary alcohol, and this is strong base. So at this stage, elimination. Let me see. Now, actually this rank cannot occur. This rank cannot occur because there's no heat. There's no heat. So why? Because this oxygen, this OH group is a very poor leaving group. So this reaction cannot occur. This is very poor leaving group. Hydroxide is a very poor leaving group. Okay, and we need to use acid to catalyze. But here is this no, this just won't work. This just won't work. OH is very poor leaving group. So question 5. Question 5. So So you see, this is epoxide, and what is acid catalyzed, right? There's a proton there, and then proton, and then this group, negative group. Because this is oxygen, right? Then this carbon is partially positive, and this carbon is partially positive. And then it's acid catalyzed ring opening reaction. Therefore, this group will attack which one? Will attack this group. It's acid catalyzed. If it is under base, we will discuss the base catalyzed ring opening in another question. So when this attack here, this bond will get broken, and this will leave minus, will carry negative charge, because this oxygen will take 2 electrons and leave. And then what we can get is this. Negative. And then it's in acid condition, right? And then this negative charge oxygen can easily grab 1 proton from this. So the answer should be C, the third one. The answer should be C.